We're going to take a look at section 1.1. This section is one of the most difficult sections, I believe, in the entire course. And I know that's tough to hear right off the bat, but the good news is that if you can handle this section, then you can really just be encouraged to know that you can handle the rest of the course without any problem. So my encouragement to you is take a deep breath and just take good notes. And there's going to be times when I'm going to encourage you just to put the pencil down and just kind of listen. So please take that advice as well. So this whole section is about problem solving. And so the first thing is that we are going to look at a problem solving strategy. I have 6 steps in a problem solving strategy. You should have some notes that you can find in the Canvas shell. Feel free to print those notes out and follow along. It should make everything a whole lot easier. The first step is to read the problem. Then I suggest that you reread the problem. A lot of times we just kind of glance over a problem. We read over it too fast. Read it as many times as you need to until it makes sense to you. Then prepare for the answer. So a lot of times we skip over this, and this is a really important question and part of the question. And so if the question is asking you to find the number of shoes, then write at the bottom, write a blank and write shoes. If it's asking you to write the time, then you need to find out, is that time supposed to be in seconds or is it supposed to be in hours? So write a blank and then write hours or seconds. If it's supposed to be the number of feet or the number of inches. So that's what I mean by prepare for the answer. Underline, highlight, or write facts down. This is a very important part, and it goes right in with number 5, which is to plan, draw a picture, and solve, look for patterns. So these 2 are one of the most important steps that will help you solve any math problem. So you're going to go through that problem, you're going to underline, you're going to write down any facts that you can. A picture is worth so much in solving problems in math. And so before you actually just try to jump in and solve a problem, draw a picture, write as much down as you can. You don't have to be an artist. Stick figures, chicken scratch. I mean, just anything. Tick marks, that works great too. Just anything to help you understand the problem. And then finally, check and make sure, did you actually answer the problem correctly? Does your answer actually make sense? So that is a big part. So those are the 6 steps to the problem solving strategy. So the big thing here is, does your answer make sense? So a second ago I said, find the number of shoes. Let's say that you had a problem that said, how many pair of shoes did Andrew sell at the shoe store on a given Saturday? And let's say you worked the problem out and you found that he sold 450,698 pair of shoes. Now, I don't know about you, but that just seems like, I don't know, it's a little iffy that he probably did not sell 450,698 pair of shoes. So probably I might have made a mistake somewhere. So let's go back and rework that problem again, because probably I made a mistake somewhere, because that just doesn't make sense unless he's a really good shoe salesman. So again, just kind of ask yourself, does that make some common sense as well for the problem that you are working? All right, so just some questions to kind of ask yourself. Okay, so we're going to look at several different problems, and we're going to go through these problem-solving strategies. All right, we are going to start off the bat with one of the hardest problems in the course. So this is a problem that I want you to put your pencil or pen down. I really do mean it. Put your pencil down right now. I want you just to watch because this is a difficult problem to try to take notes with. It's much easier for you just to watch it. So I want you to watch it on the screen, and then if you so choose to go back and replay it, then I want you to take notes on it again. So you will actually see this particular problem a couple of times in the notes. So you'll have a chance to actually take notes on this a couple of times. So this time I want you just to watch it. All right, so let's use our problem solving strategy. We're going to read the problem. Melissa lives at the YWCA, which is point A, and works at St. Francis Hotel, which is point C. She usually walks to work. How many different routes can Melissa take? Note, backtracking, no backtracking is allowed. All right, so I read the problem. We're going to reread the problem, and as we reread, we're going to kind of make some notes, underline, ask some questions, things like that. So I'm prepared for the answer here at the bottom. The question was how many routes? And so down at the bottom, I went ahead and put how many routes. So that way I know that that's what I'm looking for. So she lives at the YWCA, so I put a circle at point A. She works at point C, which is St. Francis Hotel. It says that she walks to work. That doesn't seem to be too important. How many different routes can she take? This no backtracking is allowed is a little questionable to me because that's not something that I was very familiar with. So I'm going to have to research that. And so I want to explain that to you. So I'm going to research that for you and explain it to you. So what I did is I kind of blew this map up and I realized that it is not good image quality, but it will work so that we can go through this problem together. All right, so we just have the point A and point C and I eliminated everything else. So the first thing I want to do is explain backtracking to you. So to get from point A to point C, I could go down this street and then I could turn. Now, if I was really confused and I forgot something and I turned back, that would be called backtracking. Anytime you turn back towards your starting point, that is called backtracking, and that is breaking the backtracking rule. So you can never turn back towards your starting point. All right, so that is backtracking. All right, so hopefully that explains backtracking to you. So now that we understand backtracking, let's look at some routes to get from A to C. So one route would be to go all the way down to, maybe that's Geary Street, and then turn and go all the way over to the St. Francis Hotel. It's a pretty straight shot. So that would be one way. We could also go straight across, whatever that street is, and then go down. So the blue route, and that would also get me there. No backtracking on either one of those routes. We could take this yellow route, go to Post Street, cut across, go down, and across. Now, even though that's several turns, there was no backtracking. I never turned back towards my starting point. So actually, that's a legal route. So that was 3 different routes. So as you can kind of see, there's a lot of different routes here. And what I could do is just kind of just process of elimination, just try to find all of the different routes, or I can try to mathematically figure out a way to come up with these routes. So that's what I'm going to do. All right, so let me clear all this out and let's kind of take a look at this. So to get to this little corner right here from point A, there is only one way to get to that corner, straight across. All right, hopefully you agree with me on that. It turns out to get from point A to that second corner, there is only one way to get to that corner without backtracking. It's just straight across. Hopefully you agree with me on that. Now I can go down, and it turns out that those corners, there is only one way without backtracking to get from A to both of those corners. And that would be the only way to get to those corners. All right, now I want to look, if I combine those two corner routes together, and then I look at this corner route, it turns out that I can combine both of those routes together to get to that number 2 corner. And those are the two routes that I could take to get to that corner route. So to get to that number 2 corner, that would get me, so to get to this corner, I can take either this route or I can take this route. So that's why there are two routes to get to this corner. Okay, so then I can combine, if there are two routes to get to this corner and one route to get to this corner, I can combine those routes together and guess how many routes there are to get to this corner. Probably there are going to be 3 routes to get to that corner. So you're going to see that corners play a very important role in this particular problem. So now if I look at these pink corners, so these 2 pink corners are going to play in this corner right here. Okay, so if I combine those 2 corner routes, I'm going to get 3 corners. All right, so now I have the 2 corner routes that are going to give me my C, which is the problem that I was looking for. So I can combine those 3 and the 3, which are in yellow, and they will give me that there are 6 routes to get to the C, which is St. Francis Hotel. So there are 6 routes to get to the St. Francis Hotel. All right, so my question and problem for this one is that there are 6 routes. Now, I could have just kind of process of elimination, tried to map out all 6 of those routes. And that would have gotten really kind of crazy, and I probably would have missed one along the way. But instead, this was another way that I did that with hopefully not missing anything. So it turns out that the reason I was able to do this was because of a man named Pascal. So Blaise Pascal was a famous mathematician who created something called the Pascal's triangle. And he realized that there was this really neat mathematical connection between these numbers when you lined them up in this particular order. And so he created what is called the Pascal's triangle. And so if you kind of see here, we have ones that go along the corner, outside corners here. And then you will take each of the 2 corners and add them together to get the one in the center. So 1 plus 2 is 3. 1 plus 3 is 4. 4 plus 6 is 10. 10 plus 10 is 20, and so on. So it turns out that the way that we talk about Pascal's triangle is that it's divided into rows, and there are infinitely many rows. This thing goes on forever. So we have like the 0 row, the first row, second row, so on. And then you also have diagonals. So the diagonals go this way in the diagonal fashion, and they are also numbered. And so in your homework, you actually have a question that will ask you something like this. It'll say, what are the numbers of the fifth row of Pascal's triangle? So if you look for the fifth row contains these numbers right here. 1, 5, 10, 5, 1. And so you would write them in a list like this. And then you might be asked, what are the numbers of the second diagonal of Pascal's triangle? Now, the diagonals are going to go on forever. Those numbers are going to just continue on and on forever. So when you write those, you would actually write those like you see here. So you have 1, 3, 6, 10, 15, 21, and then you would write these 3 dots at the end to show that that just continues to go on and on and on and on and on forever. Okay, so Pascal's triangle, this is actually in your textbook, which you'll find in your online version of WebAssign. So this is in your homework section, you'll find this diagram. All right, so this Pascal's triangle is also going to help us to answer some more questions. Okay. All right, so as promised, here is that So I'm going to clear everything out, get rid of all of the circles. We are now going to look at this little intersection. This little guy, the first time I worked on this problem years ago, gave me fits because he's this little alleyway. And that little alleyway just threw a kink in my schedule and I didn't know what to do with him. So I really just had to think about it. But it turns out that there is only one way to get to him. And that is right there. There's only one way. That's the only way you can get to that little alleyway intersection. I call that an alleyway because I don't know what else you would call this right here. This is what I'm calling an alley. I mean, this is like a street to me, so I figure that must be an alley. That's like one of those places you don't go, you know, like in Birmingham or something. But anyway, I live in Alabama, so Birmingham or Mobile. New Orleans, New Orleans. Yeah, you don't go down those little roads right like that. Okay, so but here, so this is the only way that you can go without breaking a backtracking. So I was just like, well, that has to be a 1 right there. I mean, there's no other way. That has to be a 1. All right. So then I looked at if that's a 1, then I combined that 1 with that 4 to give me 5 at that intersection because there was no other explanation. I mean, that would be the only way. So it made sense. Okay. So then if this was 5, then this little alleyway has to be a 5 because there's no other way to get to it other than the same way you get to these right here without backtracking. So that was a 5. So then I combined those two guys and got 15 for that. All right. So I was satisfied with that. And then I came to this big street. And this is where everything changed because, like, to get to J, because now I had to take into account all of these little alleyways, intersections, and it became different. Do you see how this is different? Like, these little alleyways started getting in my way because, I mean, these are big intersections, but now I have like big intersections and little intersections, and that just messed with my mind. But I had to do something with them. So let's see what we're going to do with them. All right, we can do this. Okay, so we're going to take a look at this little, whatever you want to call this, alleyway, intersection, whatever. All right, now to get to this guy, you had, so I went back old school and I'm just like, okay, let's just figure out how you get to him. So the only way to get to him, so we have purple route, that's one way. And then we could go, you know, the dangerous way through the little alleyway. We could go blue way if you wanted to risk your life, but it's legal, no backtracking. So, so that was 2 ways, and that's the only 2 ways you could go, but that is legal. Both of those are legal ways. So that was 2 ways. So if that's 2 ways, then that must have come from 1 plus 1. So that's where that 2 came from. Okay. So if that's the case, then I would combine 2 and 5 to give me 7. And then what would I do for this? What do you think? For this little alley intersection dude. I would combine, what do you think? Yeah, I would combine 7 and 5 and get 12. And then these numbers are fixing to get really big. What do you think I would do here? I would do 12 and 15 and get 27. Okay, so clean this up. Now, this is where I'm leaving it with you. And this is where you are now going to finish this problem. But I think you can do it. No, I know you can do it. All right. So what you have to do is you now have to find this last street. Okay. You have to start with this one at the top. How are you going to find this one at the top? You are going to say this corner plus this corner. So this one right here is going to be a what? It's a what? Do I hear all of you saying yes, Miss Baker? It's a 3. Yes, you're right. It is a 3. I helped you out. Okay, so you would combine these two here to get this one. So you got to start with this one and build your way all the way down, okay, to get to J. So once you get this one, then you combine these two to get this, these two to get this, then these two to get this. Be very careful. Double, triple check your adding, okay? All right, I know you can do this one. This is one of the hardest problems in the entire book. If you can get it, I know you can. I know you can get it. So make me proud and get this one and put it behind you. Frame it. Like frame it. I'm serious. Frame it. Show it to your kids and say, look what I did. Some of you won't have kids, but anyway, maybe you'll have kids one day and say, look what I did. Okay. All right. That's it. That's the hard problem. Now we're going to move on. Okay, number 10 is another homework problem that my students, some have a hard time with. These problems, they start out, I think that the book tries to tease you and it says this is not a typical math problem, but is a problem that requires only common sense and sometimes creative thinking. Now, I just think that they're teasing you on this because these are, I'm not going to just tell you, they are difficult problems. And so, anyway, so I'm just going to tell you they're difficult problems. All right. At 4 o'clock, the grandfather clock struck 4 times. If it was 30 seconds between the first and last strokes, how long will it take the same clock to strike 10 o'clock? All right, so I read the problem. Now I'm going to reread the problem and kind of make some notes. At 4 o'clock, the grandfather clock struck 4 times. If it was 30 seconds between the first and last strokes, how long will it take the same clock to strike 10 o'clock? All right, now I prepared for my answer. My answer is how many seconds, because it says how long will it take? How long is a measurement of time? How did I know they wanted seconds? I know they wanted seconds because it says they're giving all of my measurements here. They gave me time in seconds, and whatever time amount that they gave you in the problem, that's how they want the answer. So I knew that the answer needed to be in seconds because it says how long. So long needed to be measured the same way in seconds. Okay, so how long will it take to strike 10 o'clock? Okay. All right, so what I'm going to do is I'm going to actually kind of create a diagram, my chicken scratch diagram, to figure out what's going on here. So I'm given information here that says at 4 o'clock, the grandfather clock struck 4 times. So let's take a look at this. Here's strike 1 time, and then there's a pause. Strike 2, pause, 3, pause, 4 times. Okay. Then between the first and the last time, there was 30 seconds. That's what it says, 30 seconds between the first and last time. Now, it is very tempting because in our brain, we hear 30 seconds and we hear 4 times. And what everybody wants to do is they want to say 30 divided by 4. But that is not really what has happened because, and this is where my little diagram is helpful, because you have a strike and then a pause, and a strike and a pause, and a strike and a pause. So it was 30 seconds between the first and the last strokes. Okay, so really this little arrow probably should have been more like, instead of being right here in the middle of the X, it should have been like right here and like right here. So it should have been like X, and then my arrow should have started, and then my arrow should have ended, and then it had another thing right here. That would have been a little bit more accurate. Okay, because it says between the first and the last strokes. That's what that means. So that means that the 30 seconds started at the beginning of the pause and ended at the end of the pause. So really, what I ended up happening was that I had 3 pauses in these 30 seconds. Okay, so I had 3 different sections that was divided up, 3 divisions. And that's what ended up happening in that 30 seconds. So if you look at that, I had at 4 o'clock, I had 4 dings. Don't you like how I put that? 4 dings, which that's what it is. Ding, 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 ding. And then I had 3 pauses at 10 seconds each for 30 seconds. So now I want to look at what happens at 10 o'clock. At 10 o'clock, how many dings am I going to have? 10 o'clock? Okay, class, help me. How many dings? 10, right? 10 dings. Would you like to ding with me 10 times? I'm not going to do that, just so you know. Okay, and then how many pauses? So if you had 4 dings and 3 pauses, then you're going to have 10 dings and ding, 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 9 pauses, right? And you should have the same number of seconds in those pauses if it's, you know, a legit grandfather clock. So you would have 9 pauses at 10 seconds. So it should be 90 seconds. Okay. If that doesn't make sense, push replay. All right. That's how I interpreted this. Okay. Homework number 13. Number 13, a boy cyclist and a girl cyclist are 10 miles apart and pedaling towards each other. The boy's rate is 2 miles per hour and the girl's rate is 8 miles per hour. There's also a friendly fly zooming continuously back and forth from one bike to the other. If the fly's rate is 7 miles per hour, by the time the cyclists reach each other, how far does the fly fly? How far does the fly fly? That's pretty funny. Okay, so we have read this. Doesn't this bring back terrible memories of taking like a standardized test? Yes, it does. Anyway, I'm sorry to bring back these terrible memories, but it does bring back bad memories. So, all right. So you have this picture given to you, thank goodness, of what's going on here. Let's underline a few things. They are 10 miles apart. They are going towards each other. Okay, that's important that they are pedaling towards each other. We have the boy going 2 miles per hour and the girl is 8 miles per hour. I find that a little humorous that the boy is going so slow and the girl is going so much faster. And then you have a fly that is going back and forth between the two of them, which is rather humorous when you consider that they are 10 miles apart and it is just one fly. But anyway, anything can happen in a math problem. So by the time the cyclists reach each other, how far does the fly fly? Okay, so to prepare for the answer, we are looking for the fly's miles. How did I know that it was the miles? Because everything is given to me in distance in the problem in miles. 2 miles, 10 miles. Thank goodness they gave them all to me in miles, because if they're not all the same, you have to convert them all to be the same, but at least they gave them to you all the same. So that's good. All right, so we got everything the same in miles. All right, so we're going to make this as easy as possible, and everything is given as miles per hour. So I am going to just do this very simple, and we are going to say after 1 hour. Where is everybody at after just 1 hour? Okay, so let's look at 1 hour. So after 1 hour, the boy has gone 2 miles in. All right, so after 1 hour, because he's gone, he travels at a rate of 2 miles per hour. So 1 hour, he would go 2 hours or 2 miles. All right, now the girl is traveling at 8 miles per hour. So she would go 8 miles because she would travel for 1 hour and she would travel 8 miles. Now, if you remember, they were only 10 miles apart. So if the boy goes in 2 miles and the girl goes in 8 miles and they were only 10 miles apart, then my goodness, after 1 hour, they are going to meet. Okay, so look at the question. It says that by the time the cyclists reach each other, they're going to reach each other in 1 hour. How far does the fly fly? So the fly is only going to have to fly for 1 hour. Well, how far does the fly fly in 1 hour? The fly flies 7 miles per hour. So this turns out to actually be an easy problem. The fly flies 7 miles. Thank you, Lord, for an easy problem. Now, that did not look like an easy problem to begin with. And it really, when I read it to begin with, it didn't seem like an easy problem at all. It was very confusing. But by the time I took the time to really write all of these things down and kind of look at the picture and dissect it, it turned into an easy problem. So it's not so bad. All right, good deal. Let's go to the next one. Okay, now this is going to seem like it is not even a math problem. It is more like a logic problem. So in a different language, Xander Crew means pink flamingo. Now I'm not going to read through all of this first. We're going to take it very slow and go through this one part at a time. Okay, so Xander Crew means pink flamingo. This is where we're going to be interpreting some kind of unknown language, but we're using mathematical logic to do this. All right, so Xander Crew means pink flamingo. So here's what I did. So Xander Crew means pink flamingo. Now, I don't know which one of these. One of these means pink and one means flamingo, but I don't know which is which. All right, so I don't know which is which. So I just gave you a pink blob and a flamingo. All right, then it says the meaning of Bach Paming Crew is tiny pink duck. Okay, so here's tiny pink duck, Bach Paming Crew. Now, I do see something that is sticking out to me, and I hope it's sticking out to you, is that I see this crew. All right, so from here, crew and crew, that means there's a similarity. And I see this right here is a similarity. So that means to me that that must mean crew. All right, so I'm going to go ahead and label that. That has to mean crew. Okay, and then Paming chic means tiny car. All right, tiny car means Paming chic. All right, so now I see paiming, and that means that tiny has to mean paiming. Okay, so I'm getting somewhere. What are the words for pink car? So pink car. Well, I know that pink is, right? Pink is crew. So I know that one is crew. But what is car? Well, here's my car. I know that paiming is this little, that right there is tiny. So that must mean, by process of elimination, chic has to mean car, right? So pink is crew and chic must mean car. So that's the way I did that. Crew, chic. All right, that's homework number 14. You've got one similar to that. Okay, now, last one. Finally, one that actually looks like a math problem. How many divisors does the number 8 have? To give you a reminder of what does divisors mean. Divisors is, they are numbers that divide evenly into a number, okay? So if you look at the number 8, the number 1 will divide evenly into the number 8 without any remainder. So if you were to say on a calculator 8 divided by 1, it would tell you 8, and it has no remainder, so no decimals after that. So 2 is also a divisor, 4 is a divisor, and 8 is a divisor. So it turns out that 8 has 4 divisors. 1, 2, 4, and 8. There's 4 divisors. Okay. Now, then you have a question that says, list all the numbers less than 12 that have exactly 2 divisors. And this is how it's listed in your homework. Enter your answer in a comma-separated list. Now, this is something that the WebAssign software is very, very picky about, okay? How you enter your answers. And so I'll share with that in a second. So let's talk about the numbers less than 12 that have exactly 2 divisors. So first of all, the number 1 has 1 divisor, and it is just 1. That's the only number that is a divisor. The number 2 has 2 divisors. So I'm going to add it to my list down here at the bottom. The number 3 has 2 divisors, 1 and 3. So it goes in the list. The number 4 has 3 divisors, 1, 2, and 4. So it does not make my list because it can only have 2. So to save us some time, I'm going to complete our list. So here's the rest of the list. 2, 3, 5, 7, and 11. Okay, so now how you see that is exactly how you need to type it into the computer. 2, 3, 5, 7, 11, if this was the question. So no extra spaces, no anything else. Exactly like that. Just 2, 3, 5, 7, 11. Where my students mess up is they put a period at the end, or they put in some extra spaces or something. Just remember that a computer is grading this, and so all the extra stuff, it will count it wrong. So just make sure, like if it tells you to give your answer into 2 decimal places, you have to give your answer as 2 decimal places. So, you know, however it tells you to give your answer, that's very, very important. All right, that is section 1.1. If you have any questions, please, please, please reach out to me. Good luck, and I will be praying for you.